everyone, this is Manny here, and welcome to this lesson on infinite limits. Infinite limits are limits at a value c for which the answer is infinity or negative infinity. We have taken a look at these in one of the previous lessons and we mentioned them, but now we'll focus exclusively on these types of limits. Okay, the first thing we're going to talk about is definition, or rather, the relationship between infinite limits and vertical asymptotes. Remember that vertical asymptotes are those are where the function tries to approach and either ends up blowing up in a positive direction where it reaches positive infinity, or it approaches it and goes downward and increases, and it becomes a larger number, but in the negative direction. Okay, so those are vertical asymptotes. Now, what do these have to do with infinite limits? Well, first of all, this is the notation for the infinite limit. It's just a basic limit, but the value is equal to positive or negative infinity. So if you're approaching a value x equals c, and let's say for the first part from the left side, then you would say the limit as x approaches c from the left side is going to be positive infinity. These are one of the cases where we said we could say it does not exist, but it'd be better to just say plus infinity. And that's what we're going to be doing in this section. We're just going to be writing these as infinite limits. So you can approach from the right side or left side, it doesn't matter, or you can just do the overall limit, and if you get either positive infinity or negative infinity, that's also a vertical asymptote. So, for instance, if you had a function that looked like this, and you're approaching c from the left side, then this is going to be positive infinity. If you're approaching c from the right side, this is going to be negative infinity, right? The limit. But what happens if you're doing the overall limit as x approaches c? Well, remember, for the overall limit we need to evaluate both sides. But since they don't agree as to which type of infinity they're approaching, right? Then we say that does not exist. Okay, so this is kind of important because in the examples that follow, we'll have does not exist. But that doesn't mean you don't have a vertical asymptote. It just means that the one-sided limits happen to not agree in this case. So in the case that they both agree, for example, like this, if they go like this, then in this case, if you approach from the left or the right side, the function blows up in positive infinity. So we can say that the overall limit is equal to infinity. Okay, we want to talk about some important properties of infinity, because this will help us manipulate limits whenever we're trying to find an answer. So for example, for the first property, if you take infinity and say add it or subtract it to a number, then you're going to get infinity, because it doesn't matter what the number is. As long as it's a constant number, infinity plus a number is just infinity, or infinity minus a number is still infinity. Now if you try to multiply like 2 times infinity, that'll still give you infinity. If you do negative 2 times infinity, that'll give you negative infinity, because a negative value times a positive value is going to give you a negative value. If you did negative 2 times negative infinity, that'll give you positive infinity. Negative value times a negative value is positive. Now if you're doing infinity divided by a number, in this case you have a positive value divided by positive value, so you're going to get positive infinity. If it's infinity divided by negative 2, it's negative infinity. So basically the sign, the rules for operations with signs are still in effect even if you're dealing with infinity. So, if you're dividing a positive with a negative or multiplying positive with a negative, you're still going to get a negative answer. If you take a number and divide it by infinity, no matter whether it's positive or negative 2 in this case, or it doesn't even matter if it's plus or minus infinity, you're still going to get 0. And that's because imagine what happens as the denominator grows and grows. So let's give you an example. We have 2 over x, right? And we're letting x approach, we're letting x get bigger and bigger. So what happens is we get 2/3, 2/4, 200th, and note that as the denominator increases, the value of the fraction decreases. And eventually the value of this fraction will dwindle down to 0 when we reach a denominator of infinity. And that's why the property D states that it's equal to 0. Now, property E, if you add infinity to infinity, you're going to get infinity. Now, if you subtract, if you do positive infinity and then minus infinity, it's going to be indeterminate. Why is that? Well, we're not sure if infinity minus infinity will give you 0. So we could have infinity minus infinity would be 0. We're not sure if that's going to be the case, right? We're not sure which infinity, in a sense, is greater, right? This infinity could be greater, in which case we'll have negative infinity, or what happens if the first infinity happens to be greater and you get positive infinity. So there's ambiguity as far as what case this belongs to, or even if we get a number. So therefore we say that this case is indeterminate. Just to put it in simple terms as to why this case is indeterminate. Now, for property G, if you multiply infinities, you're going to still get infinity, and the sign of the infinity depends on the signs of both of them. So if you take a positive infinity times positive infinity, you get positive infinity. Negative times negative is positive infinity, and if the signs are different, then it's going to be negative infinity. However, if you're dividing infinities, that's also indeterminate. How do we know if it belongs to the case where it's 1? Or how do we know if the numerator happens to be bigger than the denominator and we get infinity? Or how do we know if the denominator is actually bigger and we get the property that it's 0? It's ambiguous, so we say that it's indeterminate in this case. Okay, let's work out the first example. Remember, we talked about the relationship between vertical asymptotes and infinite limits. Also remember that from algebra, in order to find the vertical asymptote, for a rational function, we take a look at the denominator and see where it's going to be equal to 0, right? So in this case, from algebra, we know that we set the denominator equal to 0, so we have x minus 4 equals 0. And you solve that for x, and you get x equals 4. So we know that there's a vertical asymptote at x equals 4. But we want to take this a step further, and we want to look at how the function behaves from both sides of this vertical asymptote. Okay, so what we're going to do is we're going to take the limit as x approaches 4 from the left and right sides. Okay, so, and let me just write the function out here. Okay, so one easy way to do this is you're approaching 4 from the left side. So you want to basically kind of plug in a value that is to the left of 4. So like 3 or 3.5, anything that is to the left of 4 on the number line or smaller. So what we can do is we know that if we plug in, like, say 3.5, for example, we're going to get a negative number, right? We're going to get negative 0.5. And that means that we know that our answer is going to be negative. Now, negative what? Well, remember that this is a vertical asymptote, so it's going to blow up. So therefore, it's either going to be positive infinity or negative infinity. Now, since we know what sign it belongs to, we can just put infinity here and know that we're approaching negative infinity. Okay, so the trick is to follow the one-sided limit, do what it tells you, plug in a number that is just to the left or to the right, depending whether this is a minus or plus sign, and then determine what the sign is, and then just put infinity. Okay, so for example, we're going to do it from the right side now. So if you plug it in from the right side, the plus sign says from the right. Therefore, we plug in a number just to the right of 4, some kind of number like 4.1, for example, and we end up getting a 0.1 in the denominator, which is going to give us a positive number. So therefore, we're going to say positive, and then we know that since this is a vertical asymptote, that this is going to blow up, so it's going to be positive infinity. So it's pretty easy to determine these. You just figure out what the sign is, and then just put infinity. Now, how about the overall limit? So we know that the overall limit, or for the overall limit, we look at both cases, right? The one-sided limits. But they don't agree, right? One is negative and one is positive infinity. So we'll just say that it does not exist. Okay. In any case, because these approach infinity, we have a vertical asymptote at x equals 4. Okay, let's take a look at the second part. So if we, from algebra, we want to figure out where the denominator is equal to 0, right? So we'll just factor. When we factor the denominator, we get x plus 3x minus 3. Right? So we set that equal to 0. And we end up getting that x equals negative 3 and positive 3, right? Because that's when this is 0, and then 3 is when that will be 0. So we have two vertical asymptotes. So we clearly know what they are. Now let's try to evaluate the one-sided limits for both of these cases. So if we do a limit as x approaches, let's do negative 3 first. Let's do it from the left side. Okay, so remember, it's just to the left of negative 3, so we're going to plug in a number smaller than negative 3, right? So we're going to plug in negative 4 or negative 3.5. Well, here we're just going to plug in negative 4. So now, if we see if you can follow this. You're going to plug in negative 4 for every x you see. If you plug in negative 4 into the numerator, you're going to get a negative number. If you plug in a negative 4 into x plus 3, you're going to get a negative number. If you plug in a negative 4 into the x minus 3, you're also going to get a negative number. We don't actually need a number for the limit. We just want to determine what the sign is going to be at the very end. Okay, so negative times negative here is going to be positive. So that leaves us with negative over positive. Negative divided by positive is negative. So we know that this limit is going to be negative infinity. And that's all you really need to know, what the sign is. You don't actually need to know what the number is. Okay, so if you do this same approach, but we're going to do it from the right side. Okay, so you're going to plug in a number just to the right of negative 3, like negative 2, for instance. Okay, so if you plug in negative 2 into the numerator, we're going to get negative. If you plug in negative 2 into x plus 3, you're going to get a positive. If you plug in negative 2 into x minus 3, you're going to get a negative. Okay, so a positive times a negative is negative. And negative divided by negative is positive, so this is going to be positive infinity. Okay, that means the overall limit as x approaches negative 3 does not exist because both of these are different. Okay, and you can follow the same approach and use the same exact approach for the limit as x approaches 3 from the left and right sides. Okay, so for part C, remember we're looking for vertical asymptotes. So we're going to try to factor this denominator here. So the factors of 10 that add up to negative 7. In that case, that will be negative 5, negative 2. So we have x minus 5, x minus 2. Alright, and looks like we have matching factors here, so we're going to be able to cancel this out. Okay, so that leaves us with 1 over x minus 2. Alright. So what does that mean about the x minus 5? Does that mean we have a vertical asymptote at x minus 5? And the answer to that question is no, because you ended up canceling the factor, so therefore there is no longer a vertical asymptote here at x equals 5. So vertical asymptote at x equals 5 at not at x equals 5. You have what is called a hole at x equals 5. Okay, so you have a hole at x equals 5 because it canceled. Okay. However, we do have a vertical asymptote at x equals 2. Okay, so we have a vertical asymptote at x equals 2. Okay, so so now let's go ahead and evaluate the one-sided limits. So you're going to go ahead and do limit as x approaches 2 from the left side of 1 over x minus 2. Okay, so you're going to plug in a number just to the left of 2, such as 1. 1 over 1 minus 2, you're going to get 1 over a negative number. Positive 1 divided by a negative number is going to give you negative, so it's going to be negative infinity. If you do the same thing for the limit as x approaches 2 from the right side, you're going to plug in a number such as 3. And if you plug in 3 in the denominator, that gives you positive. Positive divided by positive is positive infinity. So therefore the limit does not exist for the overall limit. The one-sided limits are negative infinity, positive infinity, but the overall limit, we just say it does not exist. Okay, let's do the part D. So clearly we know that the denominator is going to be x equals 0, right? The vertical asymptote is going to be at x equals 0 because that's when the denominator is 0. So let's go ahead and do the one-sided limits for this. We're going to do 0 from the left side. Okay, so if you plug in 0 from the left side, such as negative 1 for instance, we're going to have e to the negative 1 over negative 1. Okay, e to the negative 1 is just e to the positive 1 over negative 1. E to the positive 1 is just e, and that's just a positive number. Positive divided by negative is going to give me negative, so this is going to be negative infinity. Okay, so if we do it from the right side, then let's say we're going to plug in like 1, then we'll have e to the negative 1 over 1. But remember, e to the negative 1 is nothing more than 1 over e. Okay, so that becomes 1 over e divided by 1. It doesn't matter, 1 over e is still positive. So we have positive over positive, which is positive infinity. Okay, so we're going to do the natural log example here. You may know from a previous algebra course that the graph of natural log looks like this, with a vertical asymptote at x equals 0. And that is because you cannot take the natural log of 0 or a negative number. So it is undefined. So if you want to find the vertical asymptote of natural log of x minus 1, then you simply set the argument equal to 0 and solve for x. So in this case we have x equals 1, so we have a vertical asymptote at x equals 1. Okay, now let's look at how to evaluate the one-sided limits for this case. Okay, so if you do it from the left side, then we need to plug in a number just to the left of 1, such as 0 or 0.5. We're just going to plug in 0. 0 minus 1 is negative, so you're going to have the natural log of a negative number, which you cannot do, right? So we say that the limit does not exist from that side. Easy enough. Now if you do it from the right side, then you're going to plug in a number just to the right of 1, such as, 1.5. Okay, so let's go ahead and plug in 1.5, for example. So here we get natural log of 1.5, or 0.5. Remember, natural log of 0.5, that's the same thing as natural log of half. Okay, now you may know that if you have a value here that is less than 1, you're going to get a negative log. And that's because of the following property. So you can rewrite 1/2 as 2 to the negative 1 power. One of the properties of logs is that you can bring the exponent down as a coefficient. Okay, so then natural log of 1/2 becomes negative natural log of 2. So therefore, this is telling you that this is a negative number. So if we approach 1 from the right side, we're going to get negative numbers, and this is only going to become more negative as we get closer to 1 from the right side. So this is a negative quantity, and therefore we say it's negative infinity. Okay, let's do the final example here. So we have secant x over x squared plus 1. Okay, so now if we take a look at the denominator, we know that that cannot be equal to 0, right? There is no real number that you can plug in here that will make this 0, because you're going to get x squared plus 1 equals 0, x squared equals negative 1, and then you're going to have to take the square root of a negative number, which is there's no solution in the real number system. Okay, so does that mean that there's no vertical asymptote? Well, not necessarily, because remember that secant is equal to 1 over cosine. So here we have 1 over x squared plus 1, and then the secant gets replaced with 1 over cosine. So we have to take a look at the cosine, and when cosine is equal to 0. So when is cosine equal to 0? Well, we look at the unit circle, and cosine is equal to 0 when we're here or here on the unit circle. Because remember, cosine on the unit circle corresponds to the x value on the unit circle, right? And the sine represents the y on the unit circle. So in this case, in this coordinate, we have 0, 1, 0, negative 1. So basically at pi over 2 and 3 pi over 2, we have cosine being equal to 0. As well as if we go around and around to these same points, we're also going to get 0. But in other words, we have infinite amount of vertical asymptotes here, but we're only going to be concerned with just one. So we're just going to say x is pi over 2. We're only going to look at one of them. Of course, they're infinite. You can say this plus 2 pi n, or 3 pi over 2 plus 2 pi n, where n is any number. But we're just going to be looking at pi over 2. So let's take a look at the limit as x approaches pi over 2 then, from the right and left side. Now remember, this is a quotient, so we can take the limit of both of them separately. So that's what I'm going to do here. I'm going to do the limit of secant separately, and then the limit of the 1 over x squared plus 1 part separately, and then just multiply the two, and we'll get our answer. Okay, so how do we do the cosine part? Well, let's look at how the cosine function looks like. The cosine function looks like this, right? And this right here is at pi over 2. So if we approach from the left side, note that the function decreases down to 0, but the function is still going to be positive because it's above the x-axis. So we know that this right here is going to be a positive number. Okay, so therefore we have a positive here, and then if we plug in pi over 2 here, of course we're going to get a positive. If we plug in, like, pi over 4 or something, we're still going to be positive. Positive times a positive is positive. So we're going to say that it's going to be positive infinity in this case. Now if you do it from the left side, or the right side rather, okay, so if we do it from the right side, then notice that the function is increasing towards 0, but it's still in the negative side, right? So the function is negative, so right here, this is going to be negative, And it doesn't matter if you plug in, power of 4, this is still going to be positive. Negative times positive is negative, so it's going to be negative infinity. So those are your one-sided limits for part F. Now, if you, of course, knew what the graph of secant looked like, you can also determine this, right? So if you were to draw the graph of secant, and it would look something like this. Okay, with these U and upside down U's, and this is going to be at pi over 2. So if you approach from the left side, notice that the function is increasing to positive infinity. And then if we approach from the right side, the function is decreasing towards negative infinity. And then you can multiply that by the limit for 1 over x squared plus 1, and you're still going to get the same answer. So you can also exploit that, the graph of secant, to help you with this example. Okay, so we're going to simply determine the following limits. So if we want to do it for 1 over x, remember, so we need to do the one-sided limits so that we know what the overall limit is. So if we do it from the left side, you're going to plug in a number to the left of 0, such as negative 1, and you're going to get 1 over negative 1, which is negative, right? Which means your answer is going to be negative infinity. The limit as x approaches 0 from the right side, remember, if you plug in 0 in here, you're going to get undefined, right? So that's what you really should be doing. The first step you should be doing is doing a direct substitution. In this case, you're going to get 1 over 0, which is a division error, so you're going to get undefined. Then, once you know that it's undefined, that means it's going to be a vertical asymptote. Once you establish that it's a vertical asymptote, then do the one-sided limits. In this case, I'm going to plug in just to the right of 0, which is 1 over 1, for example, which is going to be positive. So then we can say, since it's a vertical asymptote, we know the sign, it's going to be positive infinity. Okay, that means that the overall limit for this does not exist, because we have negative infinity for one side, positive infinity for the other. They don't agree, so it does not exist. Okay, for the right side, I'm going to do it from the left side. Notice that we do a direct substitution, you get 3 over 0, which is undefined, so that means it's a vertical asymptote at x equals 0, right? Which means now we can proceed to plug in a number to see whether it's positive or negative infinity. So if you plug in negative 1, for example, we get 3 over negative 1 squared. And negative 1 squared is 1, so we get 3 over 1, which is positive. So we get positive, and therefore we say that this is positive infinity. Now if we do it from the right side, we plug in a number just to the right of 0, such as 1 for instance, and we end up getting positive as well, so we get positive infinity. And that means that the overall limit is positive infinity. Okay, so now for the third example, again we do a direct substitution, plug it in for x, and we get for x here and here as well. So we get 2 over 2 minus 2, which is 2 over 0, undefined, right? So vertical asymptote at x equals 2, we know that. Then we do the one-sided limits to see if they agree. So we're going to plug in a number such as 1 from the left side. So if you plug in 1, you're going to get positive here, and you're going to get negative here, because 1 minus 2 is negative. Positive divided by negative is negative, so therefore your answer is going to be negative infinity. So if you do it from the right side, you're going to plug in a number to the right, just to the right of 2, like 3 for instance. You get positive over here, positive in the bottom, which gives you positive infinity. Therefore, the overall limit here does not exist. Alright, so let's do the log. Here we're just doing the one-sided limit, not the overall limit, so we're good here. So remember how logs look like. The graph of log looks like this. Vertical asymptote at x equals 0. If you didn't know the graph, that's okay, because you try to plug in 0 as long as you know that you cannot do log of 0, because log of 0 is undefined, right? So log of 0 is undefined, so therefore there has to be some kind of vertical asymptote. So now we're going to proceed to plug in, a number just to the left. Sorry, this should be a right-sided limit, not a... No, actually, no, it's a negative-sided limit. If you do it from the left, then you're going to get log of, say, -1, which we know that we also cannot do that, so it does not exist. If you were to do it from the right side, then if you plug in log of half, for instance, right? Log of half, then remember what we talked about earlier, log of half is the same thing as negative log 2. Which means it's a negative number. If you take a log of a fraction that is smaller than 1, you're going to get a negative number. So this is going to be negative infinity. Okay, so the last one for this example, if we were to do as the limit as x approaches infinity of tangent, the limit as x approaches pi of tangent, then you're going to get, let's do a direct substitution first. You get tan pi over 2, but then remember that tan pi over 2, that's sine over cosine, so sine pi over 2 over cosine. But remember, cosine pi over 2 is 0, right? So this is actually undefined. So we know that that's going to be a vertical asymptote of some sort, so we're going to do it from the left and right side. Okay, again, if you knew how the graph kind of sort of looked like, if you plugged in, say, x equals, anything to the left of pi, such as pi over 2, for instance, then you're going to get tangent of pi over 2 divided by 2, which is the same thing as tangent of pi over 4. And tangent of pi over 4 is nothing more than 1, so you get a positive, right? So since it's positive, we'll just say that the answer is that it's going to be positive infinity from the left side. Now if you did it from the right side, we're going to plug in a number just to the right of pi, a number bigger. So let's say 3 pi over 2, for instance, right? And you're going to get tangent of 3 pi over 4 overall. And tangent of 3 pi over 4, well, it's going to be here, and 3 pi over 4 is over here. So that's going to be a negative value, so this is going to be -1. So if it's a negative number, we're just going to say that's negative infinity, which means that the overall limit does not exist. Okay, you can also figure this out if you knew how to graph the tangent. Remember that the graph, in this case, it's undefined at pi. So if you knew kind of how the tangent looked like, which looks like this, then you have this part, and then the right side will look like that. Okay, so if you approach from the left side, notice that from the right side, you're going to get negative infinity. And if you approach from the right side, you're going to get positive infinity. So you can also determine this if you know the graph quite easily. Okay, so let's just determine the one-sided limits here. So again, we plug in the 3, right? Do a direct substitution and see if it works. Here you're going to get 3 minus 3 is 0. 0 times anything is 0. So you're going to get 0 in the denominator. So this is clearly an error. So that's a vertical asymptote. Since it's a vertical asymptote, we know it's going to be infinity or negative infinity if we do the one-sided limits, right? Here we're doing it from the left side. So we're going to plug in a number such as 2. If we plug in 2, we're going to get negative for this one and positive for this one. We have a positive in the numerator, and negative times positive is negative. Positive over negative is negative. So this is going to be negative infinity. Okay, so for part B, f of x is x squared plus 1, and g of x is 1 over x minus 1. So remember the properties of limits, that you can take this limit here, and you can break it into the limit as x approaches 1 of the numerator, and you can take the limit of the denominator separately. Okay, so let's evaluate the numerator first. If we do 1 from the left side, for the numerator, we simply just plug in 1 in for x, right? So therefore we get 1 squared plus 1, which is 2. So we have 2 for the numerator. Now let's look at the denominator. Again, we're going to plug in 1, do a direct substitution, and see what we get. So we get 1 over 1 minus 1 is 0. 1 over 0 is undefined, so this is a vertical asymptote. So we're going to plug in a number just to the left of 1 then, which is going to be like 0, for instance. 1 over 0 minus 1, we get negative. So this is negative infinity. Now, if you remember one of the properties states that if you have a constant divided by an infinity term, that's going to equal to 0. So the answer for this limit is actually 0. Okay, so we're going to do the last part here. Again, we're going to do a direct substitution to see what we get. So we get 1 squared minus 1 is 0. We get a division by 0 error, undefined. So therefore we evaluate the one-sided limits. Okay, so let's plug in a number just to the left of 1, such as 0. To summarize this lesson, we talked about a notation for infinite limits. We did it indirectly by looking at some problems and seeing how it's written. In addition, we talked about the relationship between vertical asymptotes and infinite limits. Remember, if you evaluate a limit at a value and you get infinity or negative infinity, that is an infinite limit. And that tells you that you have a vertical asymptote at that point. Now, we also talked about properties of infinity limits, more specifically of infinity itself. So we talked about some operations with infinity, such as if you did infinity times a number, it's simply infinity. Infinity plus a number, still infinity, and so on. We also talked about some indeterminate forms of infinity. in order for the calculations to be more simple whenever we do calculations with infinity. We've also looked at the graphs of some functions. We've done examples with tangent, so some trigonometric functions, as well as some logarithmic functions, in order to provide you with more varied examples. Thank you, everybody. I hope you enjoyed this lesson. I hope you learned something, and I'll see you in the next lesson.